Okay, so let's continue where we left. So yesterday we posed a problem, and the first command of the exercise was to find the demand function. So the solution is to integrate dp over dx with respect to x. So we're studying substitution for a reason. Which is that in this example it is adequate to simply propose a substitution u equal to 9 plus x squared, which means that du is equal to 2x dx, and therefore x dx is equal to 1/2 of du. So the info that we were given was the derivative of the price with respect to x. That means that we can obtain the price as a function of x just by integration. And we plug in the function for dp dx that we were given. So it's the integral of minus 135x divided by the square root of 9 plus x squared dx. So this is the reason we care about this x dx factor. I take the minus 135 out. So I have 1/2 of the u by this formula above. And then by using the substitution, this is u to the 1/2, which I can perform taking out the minus 135 1/2 factor. So I have u minus 1/2 du. So again, as usual, the substitution method lets us perform the integration in a much easier fashion. So this is equal to minus 135 divided by 2, where the integration is u to the 1/2 power, then divided by 1/2, plus a constant of integration c, which simplifies to minus 135. You have to remember that u is this, and it's to the square root. So this is the square root of 9 plus x squared, plus a constant of integration c. So, as in all integration methods for indefinite integrals, when you find the indefinite integral, your problem is determined up to a constant, which you have to determined from the info that you were given in the problem. Sometimes it amounts to an initial condition, sometimes it is related to a point that the function is supposed to pass through. And now we determine the constant c by knowing that the price is equal to 30 when x is equal to 4, so that's part of the info that we were given about the problem on last class. So P of 4 is equal to 30. And if I do the substitution, basically I have 30 equal to P of 4. Then I substitute minus 135, the square root of 9 plus x is equal to 4. So this is 4 squared plus a constant c. So this is minus 135 of the square root of 9 plus 16. This is actually a cool number, plus the constant c. So 9 plus 16 is 25, the square root is 5. So what you have amounts that 30 is equal to minus 135 times 5 plus the constant c, where c then must be equal to 135 times 5 plus 30, which is equal to 705. So this is the cool thing, that we knew this piece of information. So now we have the formula for the function, which is that p of x is equal to minus 135, the square root of 9 plus x squared, plus this constant, which is 705. And we're done with the first part of the problem. So the second part of the problem is, of course, stated over here. Is there a question? At what price will 300 units be demanded? So you have to be mindful of the units that you were given in the statement of the problem last class. And the second question is, well, what price will no units be demanded? So in the units that you were given in the statement of the problem last class, was indicated that the units for x are in terms of the hundreds. So if you have 300 units, that means that x is equal to 3. So now you know that p evaluated at 3 is equal to minus 135, the square root of 9 plus 3 squared, plus 705. And if you do the computation, it's approximately, and then putting the figures outright in dollars, 132.24 per unit. Remember that the function p is the price per unit. No units, of course there is an interpretation to that, means that x is equal to 0. So you just have to evaluate that x equal to 0. P of 0 is equal to minus 135, square root of 9, since x is equal to 0, plus 705 if you make the difference, so you multiply by 3, this is stuff. So you get 300, and in units of dollars per unit. So the last question is the following. How many units are demanded at a price of $20 per unit? Now the problem is slightly different because what you have to do is to find x. So what you have to do is to find x such that 20 is equal to p of x. And given that you have the formula for p of x, this is minus 135 multiplied by the square root of 9 plus x squared plus 705. So you only have to basically solve for x. So if we continue, you simply pass to the other side. You have 20 minus 705 divided by minus 135 equal to square root of 9 plus x squared, which, okay, you do the computation and you take the minus 685 divided by 135, so which you can square by taking the square on both sides. Is there a question? Is it focusing okay? All right. So this is equal to the square of 685 divided by 135 squared. And you simply solve for x continuing. So you have x squared equal to 685 divided by 135 squared minus 9. And you simply solve now. So you have the square root of this object. Of course, you can do the calculator, use it for the computation. 135 squared minus 9, which is around 4.09. And now the final part of the problem is that if you remember, this problem is choosing x with hundreds of units. So approximately, this is an approximate calculation, 4.0900 units. So 409 around will be demanded when the price is $20 per unit. But the main difference here is that instead of finding the p, you had to find x. However, you had the formula, so you only had to solve for it, and it is not a big issue. So that is the first approach. Of course, we chose an example where, although it's applied, the method to solve part of the problem is integration by substitution. So that is one way to show that it's actually useful, especially in these sets of problems where we have differential equations. The second, I think you will find quite interesting because it is quite applied and you have basically a dynamic model for supply and demand. So it is partly conceptual in terms of the application, and it also has some exercise. So I'm not an economist, I'm not a businessman. However, I know how to solve differential equations, and so given the model, I can solve for it. So you're probably more familiar with this. I'm not claiming to do more introduction to the intuition than what it is on the book. So this is up for you to study. But you basically will study supply and demand not in a static case, which would be the equilibrium, but when you have time dependency, which means that you might involve derivatives, and then the problem is a little bit more complicated. So you will denote by S of P the number of units a particular commodity is supplied to the market. So it will be just the supply, but I'm giving the introduction. At the price, which is P, in the units of dollars per unit. So D, which will be the demand, which is also a function of the price, will be the number of units demanded by the market at the same price. So, some introduction, which I guess is common culture for everybody. So in the static case, for market.
Can you move it over, please?
Wasn't it supposed to be already on the boundary? You cannot see? Oh, okay. Yeah, thank you for letting me know.
Thank you.
Sure. So in a static market equilibrium, so in the static case, of course, the demand is equal to the supply. Now, that is basically a equilibrium case. You can find even, well, I don't want to give too much info, but in physics you can find this kind of thinking related to gases. That's all what I will say. You can study the equilibrium case. Now, this is where nothing is changing. That's why it's the equilibrium case, which is static. But if you go to the dynamic case, if you try to study a dynamic economic model, what you have is that the price, the supply, and the demand change with time. So as far as the math is concerned, essentially you're going to give time dependence to these variables, nothing more. Okay? I mean, if you think about it, look, we're in a math course, and also we have a finite time where we are constrained to 50 minutes. So if you have noticed, when I put the statements of the problem, I always put only, hopefully, the essential information. I do not go into details into the name of the administrative director. I do not go in the name of the company, because that is useless for the sake of the math. Okay? So, and I think that is part of the usefulness of mathematics, that you become very abstract, very logical, and you extract only what is needed for the problem and nothing more. So there is a model that is stated in the book, which is the Evans model for price adjustment. And it has the following equation. So the derivative of the price with respect to time is proportional to the difference between the demand and the supply, where K is the positive constant of, well, I would say constant of proportionality, but so far this is the only thing that we know. But look, this is the equation in our social phenomena, if you want to look at it, where we have the change, or the rate of change in the price, is given by the difference between demand and supply. Okay? If you think about it in the simplest case, which would be the static case, when the supply and the demand are equal, this would be 0, which means that the price is also static. Okay? So it's some intuition behind it. Like, if there is an equality between supply and demand, there is no change in time. However, if there is a difference, then you have some dynamic, which is the change in time. Okay? So now we will do an exercise related to this model. So the statement of the problem is the following. we have a product introduced with an initial price of $5 per unit. What you're given is that t months later, so the time is measured in months, the unit price, which now will be a function of time, that's why you have P of t, will be changing at a rate equal to 2% of the shortage, which is D minus S, where the supply S of P, you're given the form of the function of supply as a function of the price, which is 23 plus P, plus 2P actually. The demand is the function d of P equal to 50 minus P. And so just as an observation, the units of the supply and the demand are both in thousands of units. And you also have a constraint that you're given for the interval, which is that basically P goes between 0 and 9. So there are different indications. The first command of the exercise is to set up and solve. And this is something that I will explain, because I need to explain what an initial value problem is. But we're asked to set up an initial value problem and to solve. This is related to the differential equation, so I will mention it in a second. Initial value problem, we will use the abbreviation IVP, and it's an initial value problem, or IVP, for the price as a function of time. So, look, this is actually material for or from differential equations. So, an initial value problem, when somebody asks you for an initial value problem, what they're asking you is for not only a differential equation, but also for an initial condition. So think about it mathematically or in terms of physics. It's an initial value problem, which means you have to solve a problem where you're given an initial value. That initial value is the initial condition. What is the description of this problem, or the equation for this problem, or the model for this phenomena is precisely the differential equation. That's why it's called like that. Okay? So if you think about it, when yesterday we presented what is a differential equation, and we solved for the exponential by means of separations of variables, what we got was the general solution. And the general solution had a constant, which was, okay, the function is equal to a times e of kt. The a is to be determined. That is the general solution for that equation. But in order to determine for an initial value problem, what you're given is also the initial condition, and then from that initial condition you determine the a. And then you do not have the solution in general, but you have it for that specific problem. Okay? So that's how the initial condition will be used in order to determine equivalently these constants of integration that we've been determining by means of the info that we're given. It's exactly that. So let me continue. We already know the dpq, we just have to do some algebra. If you notice from the Evans model, what you have is dp dt equal to a constant k times d minus s. And you only have to substitute for, well, if you remember, s of p is this, and d of p is this. So we only had to substitute for that. So you have a constant k, which we will also determine from the info, and then we plug in the information. So d is equal to 50 minus p, then you have minus s, so you have minus 23 minus 2p. If you do the simplification, this is k times 27 minus 3p. Now from the information, because you were told that the rate in which this will change will be 2%, you just express this rate, which is related to k, in terms of decimals. So this is the 2% thing. So read the statement of the problem, try to realize that you're given the info about the rate of change equal to 2%. This is why this k is equal to 0.02. And if you also notice information of the problem, you will see that the initial condition is at the time 0, the price at the initial time is 5. So, yeah, the initial price is $5 per unit. Now we do have mostly all the information, because for the initial value problem, or IVP, I need the DFQ, which we already solved. We just have to plug in 0.02 times 27 minus 3p. And, well, yeah, I mean, I could do some simplification if you want. Perhaps factorize the 3 over here, it's okay. 9 minus p, so take out the 3 over here, multiply. And then for the initial value problem, in addition to the DFQ, you need the initial condition, so which is p of 0 equal to 5. So if you have not seen what an initial value problem is before, here it is. It's a problem where you have the equation, which in this case is a differential equation, plus the initial condition, which is the initial value. Now, we chose this problem for a reason in this section, which is that we will solve it by substitution. So now we will solve this DFQ. You can pass to the other side, basically, again, separating variables first, everything related to p on one side, so you have dp divided by 9 minus p. Then you have, think of this, okay? So just simplify. And then you have the constant factor 0.06, then the integral of dt. The first one, if you realize, I mean, you would, in your mind, do a substitution, basically, of p minus 9, which would be the u. You have a minus sign. So if you do the computation, actually what you get, so be mindful of the minus, so you have minus natural log of 9 minus p. If you remember, also the constraint was that p was less than 9, so this is related to the absolute value, so you're good in terms of writing it like this. And this is equal to the integration on the other side, which is 0.06t plus a constant of integration. Now, we will use C1 because actually we will express the constant in a different form. But you have to determine the constant, the actual value of the constant from the initial value. So we can simplify a little bit. If you pass the minus to the other side and you take exponentials, you have 9 minus p equal to e of minus 0.06t times e of minus c1, which is the reason why we wrote it as c1, because we will actually substitute or define a constant c. So this is c times e minus 0.06t, where c is e of minus c1. So it's just defining a constant in terms of the previous one, it's nothing more. And we can just pass the price to the other side, which is p of t, 9 minus c, e of minus 0.06t. So far, we're almost done, except that we have to find the value of the constant, which will be obtained from the initial value. And this is determined because of the fact that we know that 5 is equal to price at the time 0. So this is equal to 9 minus c e to the 0, which is equal to 9 minus c. So that means that c is equal to 9 minus 5, which is equal to 4. And then if you write the formula, then you have that p as a function of t is 9 minus 4 e minus 0.06t. So bottom line, you determine the constant from the initial value. That's what you have to learn from this part of the problem. Now you have the actual function, and you will do the other commands of the exercise based on that solution. So the second indication is how much revenue should we expect from the sale of the product after 6 months? So you have to remember that the units of time were months. So when t equal to 6 in months, the unit price P of 6 equal to 9 minus 4 e minus 0.06 multiplied by 6. And if you do the computation, it's approximately 6.21. Important thing is that you have this value. Now, you also have to remember that the demand, D of P, is given in terms of thousands of units. So, if you consider what is the revenue, given the choice of the units, you have 1,000, then the function D of P multiplied by the price. So you have the demand times the unit price, and then converting with the 1,000 factor, okay? So, can I continue? Generated by a price of P equals $6.21 per unit. And if you do the computation, then okay, you find the revenue at the time t equal to 6 months, so it's 1,000 d of P of 6 times P of 6. So you plug in 1,000, 50 minus P of 6 times P of 6. So you have 1,000, 50 minus 650, sorry, minus 6.21 multiplied by 6.21. If you do the computation, this is equal to 1,000 times 271.936. And if you do the conversion, this is 271,936. And just to indicate what it is, this is the revenue generated after 6 months. So the final question is the following. What is the equilibrium price, P of E, so price of equilibrium, which is defined by the price where the supply equals the demand. So what is this price? So then you're also told to show that P of T approaches this value, P of E, in the long run, which for the sake of the model means that as T approaches infinity. So, well, it's asking you to solve for the static case, actually. So, in the static case, you have the equilibrium price. P of E happens when the supply is equal to the demand, meaning that, well, S of P is equal to D of P, which means the 23 plus 2PE is equal to 50 minus PE. So just this would be S of P, this would be D of P. If you simplify, that means that 3PE is equal to 50 minus 23, which is equal to 27. That means that P is equal to 9. So there is no mystery. Well, in fact, if you think about it, your dpq is defined precisely as the difference between the supply and the demand. So in that case, which would be the equilibrium case, the derivative of the price with respect to time vanish would be 0, which is part of what you are being asked in this indication. So on one hand, you have figured out the equilibrium price, which is the static solution. The second thing that it asks you to do is to verify that the price approaches this value as the time approaches infinity. So it's the limit as t approaches infinity of P of t, which is the limit as t approaches infinity of 9 minus 4 e minus 0.06 t. I should say there is a typo at the end of the book, if you notice. There is a misprint of a bad translation in this limit where I assume they copied values from some other problem, and it doesn't have to do anything with what they wrote before. So just keep it in mind. But in any case, I mean, it's kind of clear what will happen. In this limit, okay, this part is a constant, this part will decay to 0, so this part will vanish. So basically you have 9 minus 4 times the limit as t approaches infinity of e minus 0.06 times, so this goes to 0, and you end up with 9, which, oh, surprise, it is exactly the equilibrium price, right? But it's kind of like basically in the design of the problem, because the design of the problem is that the time derivative happens when there is a difference between supply and demand. What you expect, and there are some problems like that also in physics or in math, like a diffusion equation, or in statistical physics, is precisely that you have an equilibrium solution as the time approaches infinity, which means that as t approaches infinity, you expect the derivative to go to 0, which is what is happening in this case. So this is the solution, or the limit of the solution as t approaches infinity, which coincides for the case precisely when d minus s is equal to 0, which is the case when dp dt is equal to 0. That is a feature of equilibrium problems in any application. Precisely because you're assuming, or you're designing the equation such that there is an equilibrium. Sometimes there is no equilibrium. In a wave equation, there won't be any equilibrium because basically you have waves moving. It's assumed that the energy is preserved, so it never stops. In the case of the heat equation or a diffusion equation, or the equilibrium of a gas, it is assumed that you have some process where you have some energy loss or some friction, and you decay to an equilibrium. In this case, it's a little bit like this over here. So, one final point to make you notice is that at equilibrium, which is the static case, so this is just a summary of what I have told you. 0 is equal to dp dt, which is equal to k d minus s. So in the case where you have the static case, meaning if it's a static, which is equilibrium, there is no time change. It doesn't change in time in the static case. So that means that the derivative should be 0, because there is no time change. And therefore, that would mean that d is equal to s in this case, by assumption. If this equation is equal to 0, then the only case is precisely that d is equal to s for this to happen. Now, dp over dt is equal to 0.06, 9 minus p, if you notice the simplification that we did. So in the static case, also it would, I mean, it's just basically scrambled in the equation again, but to make the point obvious, that when dp over dt is equal to 0 in this expression of the equation, that would mean that p should be equal to 9, which is precisely what we're having in this time limit. And, well, I mean, there are just a couple points to consider, which are not in the book, so that's why I'll just mention it on the side. There are these kind of solutions. If you think about it, if you define a function p equal to 9, the constant function, well, this is a solution to the differential equation, actually. There is a name for these kind of solutions in DFQs, which are called equilibrium solutions, precisely because they're constant and they satisfy the differential equation. So I'm just telling you that there is more theory related to this. They're called equilibrium solutions, and for your own fun, try to substitute the function p equal to the constant 9 in the equation, and of course, it will satisfy the dpq as a constant function. In any case, we have finished the indication of the exercise, so we'll jump to the next topic. And now we'll talk about the definite integral. And this is related to the intuitive idea that the integral is related to the area under a curve that I mentioned yesterday. So we'll start a new section, which is called definite integral, and the fundamental theorem of calculus. So there's a reason it's called fundamental. It's really important because this lets you precisely use all these antiderivatives exercises that we performed a couple of classes ago to calculate areas under curves. And there is also some physical applications behind this. So far, well, basically what I have done in this course is one thing. Define an indefinite integral, which is basically the inverse operator of the derivative. Then yesterday I tried to put some idea in your head that the integral is actually related to the area under a curve. That is related to something else, which is called the definite integral. I have not made any proof so far that they are related. That one thing, the indefinite integral, which is the antiderivative, is related to this other concept, which is the area under a curve. The purpose of this chapter is precisely to show the connection between both. So the summary of this section is that the area under a curve can be expressed as a limit of a sum of terms which we will call the definite integral. So we will just make a drawing in order to pose the problem. So we have x, we have y, we have an interval, which is the interval AB, and we will have a curve, which is a curve in the form of a function y equal to f of x. There is an interval where x is greater or equal to a, but less or equal to b. There will be also an assumption, which is that f of x is greater or equal to 0 for x in the interval. This is another way to denote this interval. When you have the closed brackets, it means that you have the less equal, greater equal. Okay, yeah, what else to say, of course? Well, not only the function is positive on this interval, which I have drawn, but the function should be continuous. And now the question is how to compute the area under the curve. So we have a function, let's say something like this, and we care about this area. Of course, there are many assumptions, right? The function should be non-negative, f of x greater or equal to 0, that's why we have it on this side. It's continuous, it makes our life easier, and we want to calculate the area below the curve. So basically contained between this axis and this curve. So I had already put in your mind yesterday how to get at least an approximation to that area, which is, look, approximately, I can basically subdivide the interval into smaller intervals, take the height, say, of the left endpoint, and make an approximation and compute the area by bars. And hopefully, which actually will happen, as I make the size of these subintervals smaller, I will get a better approximation to the area. Of course, again, we have a limit process. And in that limit process, as the size of the subintervals goes to 0, I will obtain the area. Again, calculus is related to limit process, either in the derivative or the integral, right? So to pose ideas and how to do it, I will indicate some steps. And so the step 1 is to divide the interval a is equal to x is equal to b into n equal subintervals, meaning of equal length or width, of length, delta x equal to b minus a divided by n. And we will define something called xj, which is the left endpoint of the jth subinterval. So j goes from 1 to 2 to n. So now let's make a picture to illustrate the process, right? So we'll have n subintervals. We're talking about the left endpoint. So for the first subinterval, actually my left endpoint is this one. It is a, so a is equal to x1. Let me write here, a equal to x1. Then I have x2 over here, and so on and so on and so on. Then I would have xn, which is the left endpoint of the n subinterval, and this would be the last subinterval. Now, of course, the length, if I have done a division into n subintervals, is the length of the interval divided by n. What I will do now is to draw n rectangles such that the jth rectangle has height f of xj. The plot will make it simpler, okay? With the jth subinterval as its base. So that rectangle would have a width of delta x. So now let's go back to the picture, right? So what I will do, I will take this as my height. Then I will draw this small rectangle. Then I will do the same for this other one, and so on for all the subintervals. If you think what happens perhaps in the last subinterval, you will have this. Then let's say that you think of the point xj and the related subinterval, so the left endpoint is used, and then you will compute this, right? And so now you have the approximation of the area. It's a coarse approximation. Please let me know if it doesn't appear. But look, I have chosen the points, right? This is the first subinterval. This is the left endpoint, which is x1. I've chosen the height, f of xj, and I have drawn the rectangle. Then I go to the second subinterval. This is the left endpoint. I choose the height, and I take this rectangle. And I do the same with all the others. This is the jth interval. This is the left endpoint, xj. I have taken the height, f of xj, and draw the rectangle. And I do this also for the last one. So, of course, the approximation looks very coarse because I have chosen a size of the subintervals which is still big if you want. If you think about it in computational terms as a mesh, well, the mesh is quite coarse. However, this is not where we will stop. We will stop when actually we take a limit, which is the length of the subinterval going to 0, which is equivalent to make that n, the number of subintervals, go to infinity. So we're dividing the interval into n equal subintervals. If I, of course, get more and more subintervals, I will get a better approximation. Also, the function is continuous, so that is really helpful. Because if the function is continuous, if you look for points which are really close, the value of the function doesn't change too much either. So actually the approximation to the area is not a bad approximation as n goes to infinity. Okay? But look, at this point you're in the same, you're facing the same problem that Archimedes faced when he tried to compute, let's say, the area of the sphere by means of limits. And what he did was to inscribe a polygon, first a square, etc., and make the number of sides go to infinity. It's exactly the same way of thinking. It's a limit process. Okay? So, intuitively, of course, I mean, look, if you even think of computers right now, I mean, we have a limit to the perception of the human eye. If I show you the picture where it's smaller than the pixelage for the length of the interval, you will not be able to notice the difference between the actual area and what is represented in the computer. Of course, mathematically, you have a continuum of numbers, so that is not good enough. But the approximation at that point won't be bad for your eye because you won't even be able to perceive it. In any case, what you're going to do is a limit process. So, well, what we have now is to state what is the area of the rectangle. The area of the jth rectangle, of course, is the height, f of xj, times the length of the base, which is delta x, which is constant, which is approximately the area under the curve for the subinterval xj, x between xj and xj plus 1, right? It is the area of the bar, which is approximately the area below the curve for that small subinterval. But as I make the refinement better, I will get a better approximation. So far I have made my point into how I have to do this process, which is by limit processes of subsequent approximations, which are supposed to be better. So now, if I consider the approximation of the total area at that point, the sum of the areas of all n rectangles is basically denoted by Sn, which is f of x1 times delta x plus f of x2 times delta x plus blah, 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 up to f of xn times delta x. Of course, the delta x is a common factor because I have chosen the subintervals of equal length, so I can factorize, and this is equal to the sum of f(x1) plus f of x2 plus blah, 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 plus f of xn times delta x. And that is an approximation so far. It's approximation of order n if you want. So, is the approximation of the total area A under the curve. So, of course, I have made my claim based on intuition that as n gets closer, to the actual area under the curve as n increases. So again, in calculus, you have to think about limits. Okay? There are limit processes. So think of taking this to the limit when n approaches infinity, where basically you take more and more and more and more subintervals. And you cannot distinguish the difference between the area of these small bars and the area of the actual curve. So the area under a curve will be defined in the following way. Let f of x be continuous and satisfy f of x greater or equal to 0, meaning that the function is non-negative on the interval a, b. A less equal to x less equal to b. Then the region under curve y equal to f of x over the interval AB has an area A equal as the limit as n approaches infinity of the following object, the sum of f of x1 plus blah 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 plus f of xn multiplied by delta x. And don't forget that the delta x is equal to b minus a over n. So you have been presented at this point with the definition of the definite integral. Try to review it. If it's the first time you see it, it might not be an easy concept to buy, but hopefully it has been intuitive. Good luck.